Waves are all around us. From our sporting events, to our cartoons, and the music we listen to, well, ocean waves. Much of our current understanding of wave motion has come from the study of acoustics. Ancient Greek philosophers, many of whom were interested in music, hypothesized that there was a connection between waves and sound, and that vibrations, or disturbances, must be responsible for sounds. Pythagoras observed in 550 BCE that vibrating strings produce sound, and worked to determine the mathematical relationships between the lengths of strings that made harmonious tones. Scientific theories of wave propagation became more prominent in the 17th century when Galileo Galilei published a clear statement of the connection between vibrating bodies and the sounds they produce. Robert Boyle, in a classic experiment from 1660, proved that sound cannot travel through a vacuum. Isaac Newton published a mathematical description of how sound travels in his work Principia, released in 1686. In the 18th century, French mathematician and scientist Jules Léron de Lambert derived the wave equation, a thorough and general mathematical description of waves, which laid the foundation for generations of scientists to study and describe wave phenomena. So, what is a wave? To better explain, let's start off with vibrations. The source of all waves, whether mechanical or electromagnetic, is something that is vibrating. A periodic wiggle in time is called a vibration, while a wave is a wiggle in space and time. There are three types of waves: longitudinal, transverse, and surface. Longitudinal waves have movements in which the particles move parallel to the motion of energy, kind of like floating on a slinky. Transverse waves have movement in which the particles move perpendicular to the motion of energy, kind of like moving a rope up and down. Surface waves have movement in which the particles move in a circle, like a drop of water in a pool. Waves have a couple of key features. First is wavelength. Wavelength is the length of a full cycle of a wave from one point to the next. Think of it like crest to crest or trough to trough. Wavelength is represented with the symbol lambda and is measured in meters. Next up is the amplitude, which is basically the size of a wave measured from one point of the equilibrium up to the crest. A wave's period, denoted by the letter T, is the time taken to complete one cycle of a wave in seconds. Frequency is the number of waves to pass a point every second. As the frequency of a wave increases, the time period of the wave decreases. This is because they are inverses as seen in their respective equations. Period equals 1 divided by frequency, while frequency equals 1 divided by period. A standing wave is a wave that vibrates but doesn't move at certain points. These points are called nodes. While nodes have zero movement, the point of a standing wave which moves furthest are called antinodes, which dictate the amplitude of the standing wave. An example of a standing wave is when a wave interferes with itself, which can happen if the wave is reflected back, causing it to resonate. A harmonic is the distance between one node to the next. Every harmonic added to the standing wave shortens the wavelength by 1 over n, n being the number of harmonics. Let's talk about the Doppler effect. The Doppler effect is the perceived change in frequency or wavelength to an observer of a moving source. There are three speeds an object moves during the Doppler effect. There is subsonic, in which the object moves below the speed of sound, sonic, in which the object is moving at the speed of sound, and supersonic, in which the object is moving faster than the speed of sound. There are 8 equations used when figuring out the perceived frequency of a wave from an observer's point of view. There is a different equation for each different scenario as shown here. 4 variables must be known: the velocity of the object or spectator, velocity of the source, the velocity of sound, and the frequency. Using these 4 variables, we can find the perceived frequency. It is important to note that in these equations, f prime is the actual frequency and f is the perceived frequency. When waves meet each other, they combine their amplitudes, resulting into one wave. They combine their properties in 2 ways: constructive and destructive interference. Constructive interference is where the 2 waves add their amplitudes together and the resulting amplitude is larger than what either was beforehand, while destructive interference is when the resulting amplitude is smaller than it was before. Beats are the resulting wave when 2 waves of different frequencies interfere with each other. When you hear a wave with consistent frequency, you'll hear consistent noise. When you hear a wave with inconsistency, you'll hear the noise raise nor in volume as the frequency changes. One way to calculate at what rate the noise will change volume is to find the beats per second. This can be done by subtracting the wave with the higher frequency from the wave with the lower frequency. The resulting number is how many beats per second you will hear.